All right, so time for some policy symmetries, I guess. Last time we did game state. Yeah, well, let's just begin, I guess. Whiteboard. Yeah, so then like we basically kind of like did this thing like for all the coins, like let's take this H for example, horizontal. Then like this coin kind of flips about the vertical midline and goes here. And this line from the like kind of like so like the top right goes to top top left goes to top right, bottom leftish goes to bottom right-ish. So all the x components are basically getting flipped according to like this formula 20 minus x for h and 15 minus y for vertical for the y components, and then both of these for the composition h and v operations, and the order doesn't matter of how we apply them because the x's are touched, the y's are touched, and like each operation's like touching different coordinates, so like there's no like pollution. It's like orthogonal bases, you know. So yeah. So anyway, so the point is that like we did that for the coins last stream, and now what's left is for the policies. And again, I believe it's just like flipping, like negating, like making a negative sign for a particular component. So anyways, I guess let's just begin then. And then like we should be done. And I believe that like just like we had for connect 4, like the symmetries for the policy function, like what I'm saying is this function is its own inverse. Like that's ultimately what I mean to say. Like let's just look at like this example of like 20 minus x, right? Or like if you're just doing a flipping of one component, then like any function that's like f equals negative x, like that's its own inverse too, trivially, right? Because negative of negative like restores back to x and so forth. And like 20 minus x again, like if you look at the graph, right? Like to tell if something's in like its own inverse, you kind of like look at the line like this line right here. So, sorry. If you have like kind of like, you know, like just like a coordinate system, then we have like the line y equals x, like this line right here. Well, I should have made it in dotted, like y equals x. And then like any k minus x or whatever is like something with like the slope of -1. So like if you kind of flip it over itself, it's perpendicular to that, like that's kind of like its own inverse then, right? Like if you have some like graph here, then like to find its inverse, you kind of like flip it over that line and like you get there, right? Anyways, that's just one of those pre-calculus things. So anyways, the point is that like we're gonna do it for the arrows, right? So let's get started. Oh wait, I need to make sure I'm streaming first, or my video is being captured. So let's wiggle the terminal, wiggle it a bit before making it full screen. Okay, well, let's get started. Get status, get log. So last time we did initial untested work on symmetries for game state transformations, and then we're gonna do the same thing but for policy, right? So let's do that. Symmetry.ts, and let me also open up connect 4 just for some reference. Okay, so let's actually start for connect 4, right? So connect 4, again, we've already seen like the definition of symmetry. It just has these, it offers these 3 methods, and it's a very kind of top level class. So like we copied and pasted directly, but the actual details are in these lambdas, these transformation functions. And again, wait, no, what again? Like these 2 functions are like the same because they're like an invertible, or like it's its own inverse for connect 4, and I believe it's the same. It's going to be the same thing for BumperCoins as well. Like the like p to p prime and p prime to p, I think like kind of are the same exact function. Like for example, like if I look at flip horizontally, we pass in the game state transformation function, and we pass in like the same function twice, the same method reference, whatever, like the same function we pass in twice because it's its own inverse. So let's recap. For flip game state horizontally in connect 4, we just basically we just kind of like leverage this function right here, which is like number of calls -1 minus c. -1 is just to account for like the 0 indexing, but essentially it becomes the same as like this 20 or like this kind of constant minus like the max potential value minus x, where like the max potential value for connect 4 is a number of columns -1. -1 because if you have 7 columns, they go from 0 to 6. So 6 is the maximum you can have, like the max minus c, right? Just like the max 20 minus x and 15 minus y, right? So like that's kind of like, they're basically like kind of doing the exact same thing. For game state, we kind of use this function here and like flip the relevant coordinates in connect 4. There's only one symmetry horizontal, so you only focus on the x coordinates. Now r, the row, like row actually means y, because row is like top to bottom, right? When you're visualizing a 2D image stack. Whereas like the column is actually x, because like that's how far right you're going, right? So again, like in image stacks, like our origin, so to speak, is always in the top left corner, which is like a bit different from like bottom left, which people might be used to. Anyways, the point is that, so we've done, or like in theory, we've done the flip transforming game state using like this type of function, this type of transformation. And let's just kind of recap that. So we have a general kind of factory method or whatever that kind of makes the function, or just passes in like this thing. And here's where we actually like do the subtraction of like this 20 minus this x. Like this thing right here and that thing right there are basically like kind of like different like fixed point ways of writing like these two transformation functions, which is very similar to again, very similar to this function right here. Okay, now let's look at the policy, right? Now the policy, okay, so the policy is also using this helper function, where let's see what it does. So when you flip a policy horizontally, the first thing you're doing is you're taking a copy of the policy. Okay, that's fair. I know we have that support. We saw that last stream in the identity function, identity transformation. And then what we do is we iterate over all the moves and probabilities. And what we're doing here is we're taking the move.column index and we're just kind of flipping it, right? So, so let's start off by basically it's going to be the same thing, except this line here for horizontally flipping will be changed to like negating the what? The horizontal component, I think. Like this arrow right here, after horizontal transformation becomes this arrow. If you look at the vertical component, like that, and the horizontal component, then this thing right here is still going to be the exact same. So like the y component, vy, in the move remains unchanged, but then the vx, like this thing right here, gets negated. Oh, and also we have to flip the move index too, right? We have to flip the move index number also. So I guess that's where the subtraction, or that's where something similar might come into play. So for policy, two things. One, for policy transform, let's call that tx. For policy transform, one is negate relevant negate relevant component or velocity component. And two, which I just remembered, in fact, is alter the move in or move ID or transform. I'm not sure what the exact like formula is, but let's just derive that, right? Let's start off with horizontal. So these are the two things, and both of these are touching move. So we need something that we need some function that consumes a move. Like we need to like kind of pass in this function f of move, which does like these two things. Like we need f of move to do 1 and 2. we need like f of move to handle both of these, and to kind of like just like we're kind of like doing this right. Wait, sorry, flip policy. Like we're kind of iterating over move and probability, but notice that we don't care about the prob. We only care about the move and prob 0, which is the move. So like here we're just flipping the column ID, like we're just kind of horizontally flipping it. And that's kind of like basically what number 2 is doing, but we also have to do number 1 too. Because again, like these two things are kind of paired up. Like our velocity components are a bit like kind of, they're not even necessary. Like the move ID, again, recall that the move ID basically looks like this. Like 8, right? Where like this direction is 0, this is 1, 2, ... all the way till 7. ... till 7, right? So basically, like, if you specify the number 1, then like that kind of gives you the velocity components where like it's not a normal vector, it's a vector at the like from these numbers you can kind of like, you know, pi over 4, pi over 2, like each step size is pi over 4 or 45 degrees, like pi over 4 radians. So that gives you the angle. And then the magnitude we kind of hard code as like the maximum velocity times 0.4. And that will be like, we kind of normalize and scale it such that that's the magnitude of the vector. So from the move ID, we can kind of get the components. Now, so it's actually sufficient for the move to only have a move ID. And we could have some global map or something that kind of maps the ID to the components. In fact, we actually have that actually, like getting the direction from the ID. I remember I cached it in like some stream for an optimization. But the reason why we also have the velocity components on the move object itself, even though that's a bit redundant, like either you have the components or the ID, like those both are kind of like bijections. It's a bijection. Like if you have one, you have the other and vice versa, right? But the reason we have the velocities is so that the physics engine, which I copied, the physics.update game state function, like it assumes that the velocity components are on the move. So that's why we kind of have to have them. Now, let me kind of recap like the way that policy is used, right? Like let's just take a step back and like kind of look at how these policies are used. So from here, state to state prime, P prime to P, basically like this kind of gives you the, this P prime to P transformation. What it's doing right here is it's like kind of giving you a different policy, right? So this one is taking like the flipped policy and kind of restoring it back. So then do we actually need the move ID in this case? I mean, to do Monte Carlo tree search, we don't, but once we eventually like do training and like, or like even after this, like once we get our policies or like after we do a bunch of Monte Carlo tree searches, like for a number of Monte Carlo, like for 1,000 or however much constant number of times, we kind of build our improved policy. Now, when we build the improved policy that we sample from, then in that time in self-play, yes, we do not actually need the move ID because the only thing we need in the move are the velocity components that we can use to kind of set the, like, add on to the coin to actually apply the move, right? Like when we're actually doing apply move, we're just kind of using the physics engine stepping like 30 ticks, 30 frames, whatever you call it. So like you don't actually use the move ID, you just use like the velocity components. But eventually when we actually like kind of get our policy and we're doing training, or actually, no. So once we get our improved policy, right? So like our improved policy has the, again, like has like the edges, like the Monte Carlo edges. And then from the edges, we kind of like look at all the moves and all the weights. And then we kind of like build a policy from that, like by normalizing it. Or like given the like each the visit count, sorry, not the weights, the not the Q scores, the visit counts, and like kind of like look at like the relative like the normalized like the edges based on like the visit counts divided by like the total visits of the root node. And then we kind of like use that to build our policy, our improved policy. And then to actually take that policy from sampling from it, like sure, everything we just did, we don't need the move ID. But then when it comes to the actual training, like given the improved policy, we want to like set that as the Y, like as the like, you know, when we're like calling neural network dot fit, like the model dot fit. then we have to convert the policy to a tensor. And to do that, we need the move ID, right? Like that's where the move ID comes from. Because like we have a vector of like 2400 or whatever number of directions, 8 times 15 times 20, where 8 is number of directions, 15 and 20 are the row and the column size, number of rows, number of columns. So like our policy is represented as a flat vector of 8 times 15 times 20, or 2400. And then to actually like get the indices of like for each kind of move in the improved policy to actually take those moves and like build the 2400 sized vector, like almost all the entries are 0 basically, except for some select indices which have some non-zero values, and those non-zero values correspond to probabilities. But to get the locations of like those move probabilities to place into our policy, we need to actually like compute the index, and that's where we need the move ID from, right? We multiply the move ID to get the offset by 300, as I mentioned earlier streams. I mean, we have the formula there, so that's the point. The point is that this kind of inverse transformation, like, or wait, no, what am I saying? So it's like once we do Monte Carlo tree search, we get our policy, like, we need to make sure that the move ID is consistent with the velocities too. So we actually need it from this direction too as well when doing Monte Carlo tree search. Like, the point is that we always want the velocity components and the move ID to just be consistent with each other because the bijection. So if we're touching one, we got to touch the other. That's a very simple way of doing it. Like if we do that, then we definitely have no problems. But yeah, the whole point is that we need the actual move IDs when it comes to training it, right? So that's the same thing. And then when we're doing data augmentation, then again, we need the move IDs to match because like, you know, like state to state prime and wait, what? Wait, this should be the other way. But anyways, okay, yeah, let's just get started. Let's just get started. Yeah, let's not talk too much. Okay, so now horizontal, right? So horizontal, let's first, okay, so let's actually like build the scaffolding to actually do it, like taking inspiration from what we did last time for game state, right? So let's begin. We have a make transformation function, right? Like that. Let's just copy that kind of nifty thing. Or let's just kind of put it in the end. So now let's call this a make transform, not game state, but let's replace it with policy. So policy, and now the lambda, like here was taking a coin gives void. Now let's replace that with m for a move, right? Because again, like this function, this lambda here, which takes in a move and consumes it, returns void, just as a consumer of move, is basically like this f of move, which we're kind of doing. So then, so what's fh of move? Like we have to consider that. Like if we first do f of h, then f of v, and then I don't think we can, I mean, then f of h plus v. So like those are like kind of like the three functions we're going to pass in. But for now, let's just work on the scaffolding, right? So like we have the move, like we have the move, which and it returns not a game state to game state, but a policy to policy, right? Policy to policy. And again, we have to kind of like do the same exact changes there. Move. And again, policy to policy. I could just copy and paste the entire thing, actually. Yeah, let me just do that. Actually, no, I'm just gonna copy. I don't want to do that. Just kind of like manually substituting everything kind of makes me more comfortable because like it's preserving the one-to-one logic of the game state versus this type signature. So okay, we have a maker, and then what do we do, right? Let's kind of like look at that. We declare it and we return it. In fact, we could just inline it and just kind of like do that itself. But anyways, well, why not? So we declare something, we close the bracket, and then we just return it. So now, instead of transform game state function, we have to make this transform policy function. Policy function. just like that. Okay, so this is a function not of game state, but of policy, or policy. And it returns a policy, right? So this function is a transform policy function. So like it takes in a policy and returns the transformed policy, right? That's kind of the idea. So how does it work, right? So first what we do is we clone the policy. Oh, I see that this flip policy actually like kind of has P and not policy. So let's actually be consistent with our connect for code. Let's kind of make everything in terms of P. So it takes in the policy and it returns a policy. The first thing we do is oh wait, sorry, what am I doing? So first thing we do is we copy the policy. Or actually, let's just kind of copy everything here. What? I have to indent it to make it make sense. So first thing we do is we take this kind of input policy and we make a clone, right? Just to make sure we don't like mutate any of the, just to clone it. And then actually, okay, so first we clone the policy. That's step one. We clone the policy, and then for each move-in policy, what do we do? Well, we apply the transformation function, right? So let's kind of scroll up. Yeah, we just kind of do this, right? So let's go to line 45. Copy these two lines. Oh, not T of coin, but rather T of move of probability and 0 to get the move, right? Transform the move according to the transformation function T. Great. So now let's kind of copy like this stuff right here, right? Let's kind of like do something like this, right? Kind of copy these two lines. So now transform instead of policy, instead of coin, it'll be transform move horizontally. Would take in the move and return void. So then it takes in the move. So then flip policy horizontally so it takes in the policy, it maps from policy to policy, basically, and make transform policy function of transform move horizontally. That's the kind of lambda we pass in. Just like that, right? So like when you do make transform policy function, its input is something, so its input, right? Like this whole, wait, what? So it takes in this consumer of a move and returns a function that maps from policy to policy. So this thing, we pass it in the consumer of the move, and we get as a return type something that maps from policy to policy. And that's flip policy horizontally. Flip policy horizontally is a transformation of policy from policy to policy. So the types make sense. Okay, good. So now transform move horizontally. So how do we do that? Well, step one, negate relevant velocity component. So here, what we have to do is like Vx, like kind of like equals negative Vx, like times equals -1, right? In fact, I feel like opening it up, I want to open up move just to move.ts just for reference. And actually I want to open up fixed point too, just for reference. So move, again, very simple thing, just move ID, Vx and Vy. So like the move ID, which we added recently, kind of like has to match with the Vx and Vys. And like they're a bit redundant, but I'm just putting in everything to make the physics work. So again, like, so here's fixed point, and where's negate? Yeah, negate. So we want to make use of the fixed point's negate function, which actually it returns a new fixed point. So like in a way it's like a clone, but we're already working with a clone, so it's okay if we mutate it. Just pointing it out that like cloning might not have been, actually no, it's always good to clone, get deep copies to be safe. So okay, yeah. Yeah, when you see the word new like that, like in clone and like in here, then it's kind of like, yeah, we're creating new ones. So then move has a Vy. So you want to take move.Vy and like set it to its negation. So okay, m or move, because it's not m, but it's actually like this move. Move.Vy equals fixed point dot, and then negate, right? Dot negate. Dot negate. And what are we negating? Vy itself, right? So this takes the y component and flips it, right? And now the move ID. So let's like so right now, right? Like if we have like let's consider this one, right? Like this thing here becomes this thing, right? So the y stays the same, but the x gets flipped. Wait, the x gets flipped. Sorry about that. Yeah, the y stays the same, but the x, like from here, from pointing to right, it becomes pointing to left. So this is not move Vy. This is Vx. Yeah, that one's probably transformed vertically, which I just did. So that's step one, right? So now we have kind of flipped the relative velocity component, and now I have to flip the move ID. So how do we do that, right? So then, again, like back to this example, like this is going to be move direction of 1, right? Like if we have, remember, like from here, like we have like, so like this kind of, this thing right here, like this thing at 45 degrees pi over 4 becomes this thing, right? Like this arrow becomes that arrow, right? So basically like this right here becomes this. Wait, does it become that? Yeah, it becomes that, right? So 1 becomes 3. So let's actually do the mapping here for ffx, for ffh, right? The move transformation for horizontal. So like first we flip the x component. Yeah, vx is negative vx, which is right here. Move.vx is negative move.vx, so that's good. And then what's the move ID, right? Like the move ID. So what's the new move ID? We have to do that, right? So this is what we were trying to solve, right? So it's actually like let's map it and see if we can come up with a formula, right? So 0, so again, let's just kind of redraw this. So 0, where does 0 go to, right? Like 0 move ID, if we're kind of, if it's launching here, right? If the coin is launching this way, then when we flip it horizontally, that means it'll launch this way, right? Again, we're just flipping only the x component. So 0 maps to 1, 2, 3, 4, right? Like 0, 1, 2, 3, 4, 5, 6, 7. So this arrow here points, so again, all these lines are actually arrows pointing outwards away from the center. So 0 maps to 4, right? Okay. And then let's consider like this one here. So like 1 So the y component is the same. So it still points vertically, so it's in like the upper hemisphere. But then rather than having a bit of a right flavor to it, it has more of a left flavor to it. So this 1 goes to 3, right? So this 1, why do I have that written? Yes, so this one here goes to this one. So 1 goes to 3. Already I noticed they're summing up to 4, so I think I may have like 4 minus x or something. That could be a candidate, which jumps to mind. And vertical, right? So we have like this one here, 2, and where does 2 go to? 2 just becomes itself, its identity. It doesn't change, right? Because like you don't touch the y, this is pure y, there's no x, right? So it's only the y, and the y stays preserved, right? Like this thing circled stays circled. It's only the x one that does it. Unless, so right now my hypothesis is that like is MID equals 4 minus MID. In fact, doesn't that look familiar? This 4 minus MID looks a lot like what we commented, like the horizontal, like the 20, like whatever, like the k minus x thing was, right? Like it looks a lot like these type of functions here, actually, in fact. But let's see if this kind of function works for this southern hemisphere too. So let's consider 5, right? 5 goes to 7, right? Like this ID here, like it still will have a downward flavor for the y side. So we're still in the south hemisphere, but then rather than having a bit of a left component to it, it's going to have a right component to it, right? So, oh wait. So we did 0, 1, 2, 3, 4, and then 5. Oh yeah, these things are bidirectional. So we have done 0, we've done 1, we've done 2, and then by virtue of doing 0 and 1, we've also done 3 and 4. That's why we can directly jump to this one. So 5 kind of bidirectionally goes to 7. Because again, like this function is its own inverse. 5 to 7. So 0, 1, 2, 3, 4, 5, 6, 7. Okay, so 4 minus 5 does not equal 7, but I think mod, right? 4 minus 5 is negative 1, and negative 1... Anyways, okay, fine, whatever. 5 goes to 7, sure. And then the remaining one is 6 goes to 6. Like this last one here is its own inverse. So 6 maps to 6. So we need a function. So we need a function that kind of like, given these inputs, like given the lefts produces rights and given rights produces lefts. That's what we want. So 4 minus mid, like kind of supports all of these. Like these things, like 4 minus 0 is 4, 4 minus 1 is 3, 4 minus 2 is 2, and vice versa, 4 minus 2 is 2, 4 minus 3 is 1, 4 minus 4 is 0. So that kind of works. But then here, 4 minus 5, like, but these are the problematic ones, the southern hemisphere, right? So let's kind of, let's think about it differently. Or can we do some mod stuff? Rather than guessing, let's kind of think of what's happening, right? Like, if we have like some kind of theta here, right? If we have some theta here, then what we're kind of doing here when we're kind of flipping about this midline, right, is like we're kind of getting the same theta, but from like this 180 degrees. So like what we're doing is like if you have like, so like theta prime, the transform thing, equals like 180 or pi over just pi minus theta, right? So pi is basically 0, 1, 2, 3, 4. So this kind of explains why this 4 minus mid makes sense. So probably this is correct. But let's see what happens here. Like we have 5, and then 4 minus 5, like pi minus that, is what? So 4 minus 5 is negative 1. And then negative 1. So 7 is basically like the same thing as like subtracting 1 from that way here. So 4 minus 5 is negative 1. And do we just do mod of 8? Like mod that by 8 to get 7? I think that's the idea, right? So here's my new like kind of formula. 4 minus mid mod 8. Mod 8. Where more generally 8 is the number of durs, which is for 2 pi. And then for pi, it's number of durs over 2. So this kind of mandates that number of durs is an even number. Number durs 8 divided by 2. So that's like the general format of this mid function. And of course it works for these three because everything is less than 8. But then here, 4 minus 5 is negative 1. So negative 1 mod 8, or not less than 8. It's like, you know what I mean. So negative 1 mod 8. I'm not sure how JavaScript works. So one thing we can do to be super sure, like which works for sure, which I'm not sure the language supports, is we can do 4 minus mid plus 8 just to like make sure that there's no negative numbers, and take this whole thing and do mod of 8. And this is like the new formula that I propose. So let's check it out. For 0, 1, and 2, right? 4 minus whatever gives you the right-hand side. And if we do plus, so let's take 0, right? So 4 minus 0 is 4 plus 8 is 12. Mod 8 is 12. Mod 8 is 4. That's correct. Let's check the other one. 4 minus 4 is 0. And then 8 mod 8 is 0. So that works. Let's check it for 1. 4 minus 1 is 3 plus 8 is 11. 11 mod 8 is 3. That's correct. Then 4 minus 3 is 1 plus 8 is 9. Mod 8 is 1. That's correct. And 2 to 2, let's check it out. 4 minus 2 is 2 plus 8 is 10. 10 mod 8 is 2. So that works. And now let's see 5. So 4 minus 5 is negative 1 plus 8 is 7. 7 mod 8 is 7. That is correct. 7. Let's check for 7. 4 minus 7 is negative 3. Negative 3 plus 8 is 5. 5 mod 8 is 5. That is correct. Then 6. So 6 to 6. Let's see. 4 minus 6 is negative 2. Negative 2 plus 8 is 6. 6 mod 8 is unchanged to 6. So this function here seems to be like the new thing, the function we desire, right? So the move ID function is what, right? Something eventually mod of 8, where 8 is actually not the number. Okay, let's go back to net actually. Actually, let's do that, like the whole thing. Okay, what? Let's just kind of stick in a net here to export the number of directions. Like this. So now we're exporting the number of directions, number of move durs. So just like we import that, what we want to do here is we want to kind of yoink that also. So now we get the number of move durs, right? Let me just maybe do a check to make sure we're not using that variable anywhere. Nope, just that. So this whole thing eventually gets modded by 8, right? So eventually we take everything and then we mod that by 8. So let's so now what we do is that divided by 2. This one divided by 2 minus, and this is not fixed point. This is all just numbers, like integers, move ID. So 4 minus itself, move ID plus 8. Just plus 8 to make sure there's no negatives. Where instead of 8, of course, yeah, so it's like full period and half period type ideas. Just like this. So that's our transform horizontally function. And actually now that we have like the transform move horizontally, and then we have flip policy horizontally, we can actually create our first symmetry, you know that? So let's actually go back to, let's go to the actual symmetries. Oh wait, what? Sorry about that. We have our first symmetry, right? Flip horizontally of a symmetry, so let's kind of like do that. So we have flip horizontally if a symmetry is a new symmetry, a flip game state horizontally, which is this function right here, and flip policy horizontally, flip policy horizontally. So just now we have finished flip horizontally. The entire symmetry we're done with one symmetry. Now we just need to do flip vertically and then flip horizontally and vertically, and then we're finished with symmetries in theory. So okay, so that's flipping horizontally. So then what do we need now? Now we need something similar to this, but from transform moves vertically, right? How do you spell vertically? Let me just copy it from here. So what we're going to do here, obviously, is flip not the x's, but it must be the y's, right? And then this one. So now, like, we need a new function. So first, let's look at vertical transformations, right? So now, rather than looking at this h, we're looking at this v, right? So this coin right here, like this arrow here, becomes this one right here, right? So now the horizontal component remains the same. So now, like this one, so let's make this a square instead of an ellipse or oval. So this kind of is the same. So v of x component does not change, but the y component, rather than going straight up, now goes straight down, right? So it's clear that we flipped the y's. So that's pretty clear. Let's just take another example. Let's look at this one. It has like a downward component, and that downward component becomes an upward component, and the x component stays the same, right? So you just have to flip, you just have to negate the y components. So now let's try to derive a formula for f of v, right? So like first we do vy equals negative, negate, like do the flip right there. That's step one, flip the y's. And then we have to kind of like do some formula for that. So let's kind of do the same thing, like what we did earlier, right? We have to build a map. So 0, right, when we flip, so now we flip the y's, right? So 0, when we flip the y component, that's just itself, right? Because there is no y component, there's only x, and x gets preserved, right? We're flipping the y's. So if you have 1, so 0 vertically, wait, what am I doing? That's horizontal. So 0 maps to itself, and flipping by 1, right, vertically. So that means like whatever this vertical thing with the up component kind of becomes down, and the x becomes the same. So this kind of becomes like that. So 1 maps bidirectionally to 7, right? Like 0, 1, 2, 3, 4, 5, 6, 7. Okay. I think the answer is 8 minus, my hypothesis now is 8 minus m, the move ID. And I think that's it. And mod 8, of course, mod 8. So 8 minus 0 is 8, and 8 mod 8 is 0, and 8 minus 1 is 7. Okay, yeah. 8 minus 1 is 7, mod 8 is 7, and 8 minus 1 is 7, which is mod 8 is 7. 8 minus 7 is 1, mod 8 is 1. Okay, so I'm pretty sure that's correct. So in 0, 1, I think I got the intuition for this. Because now, like, again, horizontally, what we're doing is we're kind of like flipping about the, like, theta equals, like, we're flipping about, like, we're kind of like doing that, right? Like, we're flipping about this vertical line right here. Whereas vertically, we're flipping about this. So it's like, I don't know. I'm just used to this, like, y equals k minus x template, but I'm just getting ahead of myself. Well, we'll see if this works. I'm pretty sure it does. 0, 1, 2. So this one, 2, when we flip it about this midline now, rather than flipping about the vertical line for horizontal, we're flipping about this one, kind of goes here, right? So 0 goes to, so 0, 1, 2. 2 goes to what? 6? 0, 1, 2, 3, 4, 5. Yeah, so 2 goes to 6. And again, note that these are all summing to 8. So 2 goes to 6, 0, 1, 2, and then 3 obviously goes to 8 minus 3 is 5. So like 0, 1, 2, 3, and then 4, 5, right? Again, like for this one, we just flip the y and there is no x to concern about. And this one, it still has a bit of the western kind of side to it. But then the, instead of going a bit north, it kind of goes a bit south. So yeah, so 3 goes to 5. 3 goes to 5. And then 4 goes to 4. 0, and then 4 goes to 4. Because again, like there is no y component to flip. It's just, it's all x, right? It's all x, so like it just stays the same. Because all x means it lies on the horizontal line. So okay, this function here, as you can see, everything, like 7 plus 1 is 8, 6 plus 2 is 8, 3 plus 5 is 8, 4 plus 4 is 8, and only 0 plus 0 is not 8. But then 0 is the same thing as 0, like 8 is, 8 mod 8 is 0. It wraps around. So let's consider why. Why did these two have to add up to 8? Like we saw why they had to add up to 4 based on like this diagram right here. But now let's consider what happens to theta, right? Now we have like some theta here, some theta, and then once we kind of flip it like vertically, right? It becomes like theta from this way, like minus theta, right? Like if we go a little bit up here, sorry, not minus. So this like when you're flipping it vertically, we kind of like reflect about like going up here, we have to go down here, right? So this angle, like this angle right here, theta prime plus theta plus theta, like this whole thing right here plus like this whole thing, we're completing the cycle, equals 2 pi. Where 2 pi is the same as 8, right? As 8, like the whole thing, like 0, 1, 2, 3, 4, 5, 6, 7, and then 8. We completed 2 pi. So it's like theta prime plus theta equals 8, right? So like this plus its inverse equals like theta and theta prime the inverse. So like, so that's the same kind of recurrence thing, or like the same, not recurrence, the same kind of, yeah, just formula where like you sum both things and they have a constant sum. Because again, like more generally, if you have like x plus x prime equals some k constant, it's very clear that x and x prime are inverses. I think I briefly kind of touched upon this. Like you could kind of like pretend that this one migrates, right? If you have a plus b, like a plus b, very simple property equals b plus a, right? Like let's just like kind of use this. And we apply this to that, right? So we flip these, and this gives you like x prime plus x equals k, right? So like, if you were to let x equal x prime and let x prime equal to x, like that, like because of this, right? Like, so like here, we basically kind of like everything is in the same spot. So like we can say x equals like k minus x prime, like just from this 1 and this 2, like just from 1 alone, we can kind of get to this, right? And then since the structure of this equation is the exact same thing, then we can basically do the exact same thing here, like recopy this k minus x prime. So like k minus x prime, right? We can kind of copy that there, but then we can let x equal x prime and x prime equal x, right? We can basically flip them, right? And again, like that's kind of like the same thing as that, like structurally, like since everything is the same, but like these things, like we can freely swap them, right? Anyways, the point is that like we're seeing things like this a lot where it's its own inverse. That's all. But I'm just kind of like giving some intuition. No, never mind. So anyways, all we have to do now is kind of apply this formula, which then completes like we've done the negation. Now we just have to like do this one for the other one, right? For a vertical. So now our function here is again the same thing. We have to ultimately kind of do the same thing there, where we end up like kind of modding by that, right? So what is the function? 8 minus the move ID, the whole thing mod 8. And we don't have to do +8 again because here, like this is like the maximum you can get. So like we're never gonna get a negative number to worry about, concern ourselves with. Minus the move.move ID. Just like that. Great. So now what we have to do now is flip policy horizontally. We can do the same thing, but for flip policy vertically. Let's use a restroom, but let me just I want to try to finish this flipping transform policy symmetries, and I want to just end the stream. And then just like that. So now we have our flip vertically symmetry, which we can kind of copy from. Oh, we don't have that. So flip vertically. Vertically is flip game state vertically. Vertically, and then flip policy vertically twice. Just like that. So we've done H, we've done V. We've finished the symmetries in theory. All we have left is the composition of H and V. And like we've done it like game state. Now we just have to kind of like do the same thing, but I'm going to use the restroom right now really quickly. Okay, so we've done horizontally and vertically for transforming. Now let's just do both of them, right? Copy this. I think we can do exactly what we did for the horizontally and vertically, where we have like this thing right here, like look at line 60, 69, where it's like kind of transform, move, and then kind of like that. So in here, like this, horizontally and vertically, And then what we can do is we can just chain both of these, right? Like that. That's kind of like what I'm thinking, right? Like this. Sorry about that. Yeah, not like this, right? This is my, again, like hypothesis. I believe that this is correct, right? I believe that we can just chain both of these, like order irrelevant, because like, and I think that should do it. Like, just intuitively, my intuition's screaming that rather than like kind of doing like kind of writing like 2 lines like this, which we could do, or 3 lines for x and then y and then some move function, I believe that it's kind of, we can kind of compose both of these. Now, it may be extra kind of like, it may not be the most efficient. It might be better to just kind of like copy the logic, but like compute this third kind of math, like kind of like combine these 2 operations into like get a closed form like relationship function for a move ID transformation. But I think that like we can just kind of like use what we already have. That just feels like more stable, or just more nice to me. But let's just double check our work and make sure that like this works, right? So by doing these 2, let's check if 1 and 2 works. What are the relevant velocity components? Well, let's look here. So this thing right there, right? This kind of like thing which is like northeast, where does this map to? It maps to here, right? So like this kind of going up ends up kind of going down, right? So this thing gets negated. So we have to negate the y, and the x component, which is like, this is like the circle or oval, that's the oval, like the ellipse, whatever. And then like this is a block for like the squares are for x's and ovals are for y's, or rectangles are for x's. So this x also gets negated, right? So basically we have to negate both. That is correct. And now let's consider like the whole, so basically what we're doing is we're kind of like flipping about, like we're reflecting about this line here. That's kind of like for transposing or for doing H and V. So like this one right here, like this 1 as we saw here, which is like this direction from 1, it goes to this direction right here, right? So like 0, 1, 2, 3, 4, 5. So 1 maps to 5, right? 1 maps to 5. And then where does 0 map to? You negate both. So 0, like if you negate the y's, there's nothing to negate. So like 0, this one here would map to what? Just wait, so this one is wait, no, maybe this dotted line is wrong. So 0 goes to here, right? Sorry, this dotted line is very long. Sorry about that. Let's just scratch the whole thing. So 0, so this is 0. Then we flip the x so 0 maps to what? Right? So 0, we're flipping horizontally and vertically. Well, first we flip it one way to get this. Then we flip it the other way, it gets itself. So 0 goes to pi, or it goes to 4. So 0 goes to 4. And then where does 1 go to? So if you flip it one way, we get like this way, and then that way we get that way. Yeah, we just talked about this. So 1 goes to 5, and vice versa, obviously. So 1 and 5 are like kind of pairs. And then what about 2? I think just, so then 2, we just kind of flip that way, and there's no x to speak of. So 2 and 6. 2 and 6. These numbers are pleasing. It seems the difference is 4 all the time. What about 3? So 3, obviously we kind of like flip this one, so we're kind of going a bit down. Rather than going left, we're going right. So like southeast. Instead of northwest, it becomes southeast. And we have taken care of every single pair, right? 7, 3, 7. So it seems that like everything is kind of off by half period, right? It's a lot like 4 minus 2, but then rather than modding by 8, we're modding by like, wait, no. Okay, so here's our map, right? So let's see if this works. Hey, it's like 0, 1, 2, 3, 4, 5, 6, 7. That's pretty cool. Okay, so let's check 0. Does 0 go to 4, right? So we first do transform horizontally, then vertically. And let's say that the move is 0. So we take 0, then 4 minus 0 is still 4, plus 8 is 12, mod 8 is 4, right? So after doing this, the move ID from 0 is 4. And now we're going to transform vertically on 4. So like number of moves 8 minus 4 is still 4. Mod 8 is 4. So from 0, we've gotten 4. So 0, we've checked. Now let's check 4. So now we're kind of going like 0. When I say check, that means 0 does map to 4. That's correct. So check on 4 means 4 maps to 0. Let's verify that. So now we're kind of like doing it, but on move ID of 4. So then this one is 4, minus 4 is 0, plus 8 is 8, mod 8 is 0. So right now we have 0. And then what we're doing here is 8 minus 0 is still 8, mod 8 is 8 mod 8 is 0. So then from 4 we've gotten 0. That is correct. Now let's check 1. So 1, so 4 minus 1 is 3. So 4 minus 1 is 3, plus 8 is 11, mod 8 is 3, and then what we're doing here is 4 minus 3 is 1, and mod whatever is still 1. Wait, we got 1 to 1? That's wrong. Wait, what? Okay, 1. We're inputting 1. So 4 minus 1 is 3, plus 8 is 11, mod 8 is 3. So 8 minus 3 is 5, mod 8 is 5. That's correct. Wait. Okay, this seems to be correct. Let me just double check it. So the move ID right now is 1, and then we want to see after doing these two lines if it becomes 5. So it starts off at 1. So then 4 minus, again, I'm saying 4 because num moved is 8. So 8 divided by 2 is 4. So 4 minus 1 is 3, plus 8 is 11. 11 mod 8 is 3. So now we're kind of plugging in 3 here. Like we're taking this equation, this whole thing, and we're kind of like taking this whole thing and substituting it here. That's like the formula which we're kind of getting. So then again, so like 11 mod 8 is 3. So now this becomes 3. So 8 minus 3 is 5. Mod 8 is 5. So from 1 we get 5. That is correct. Now let's check 5. I know this is kind of a bit tedious, but once we do this, I'm just being kind of paranoid or making sure that it works. I'm being complete. So now we have we have 4 minus 5 is negative 1. Then we add it to get rid of the negative. So that's 7. 7 mod 8 is still 7. So 4 minus 5. Yeah, we're checking 5. 4 minus 5 is negative 1. 4 minus 5 is negative 1. Plus 8 is 8 minus 1 is 7. 7 mod 8 is still 7. So we have 7. Now you're plugging in 7 here. So 8 minus 7 is 1. And then 1 mod 8 is still 1. So 5 maps to 1. That is as expected. This direction kind of is here. That's perfect. And now let's try 2. Let's see if we plug in 2 and get 6. So 4 minus 2 is 2 plus 8 is 10. 10 mod 8 is 2. Then 8 minus 2 is 6. 6 mod 8 is still 6. So from 2 we've gotten 6. Good. Now let's check if 6 gives us 2. So then 4 minus 6 is negative 2 plus 8 is, what is negative 2 plus 8? 6. And 6 mod 8 is still 6. Now number of movers is 8. Mod of 6, which we're plugging in from that thing, is 2. And 2 mod 8 is still 2. So from 6 we've gotten 2, correct? Almost done, almost done. So now we're plugging in 3. We want to see if we get 7. So now we have 4 minus 3 is 1, plus 8 is 9. 9 mod 8 is back to 1. Then we're plugging in 1 to here. So then 8 minus 1 is 7. 7 mod 8 is still 7. So 3 gives us 7. That is correct. Let me just double check that. So 4 minus 3 is 1. And then 1, 9, 9 to 8 gives you 1. And then 8 minus 1 is 7. Correct. Now let's try 7. So 4 minus 7 is what? It's negative 3. Negative 3 plus 8 is 5. And 5 mod 8 is still 5. So now 8 minus 5 is 3. And 3 mod 8 is still 3. So 7 gives you 3. Okay, good. So then we're able to chain both these functions, and that works. That's good. So now let's create this new function here called flip policy horizontally and vertically. Horizontally and vertically, and that's make transform policy function of not transform move vertically, but rather the composite transposition of the move. Just like that. And now we can create our final symmetry. Like that. Flip horizontally and vertically. Is flip game state horizontally and vertically? Just like that. And then policies, we have to do this one. And I think we're now almost done. We have all the symmetries. Just put them in the list, and then I think we're done, right? So it's really cool how like we're just kind of like chaining these two for this. So everything is kind of like, everything is nice. So like everything is contingent on this factory function, right? Which I kind of lifted from Connect 4, where like first we clone it. And then like, again, like for game states, we're just kind of like focused that like the lambda we're passing in is from consumer of a coin. And here it's consumer of a move, because the policy, like whatever the weights are, like in the move of probability, like a policy is a list of a pair where the pair has a move and a probability associated with it. It's a pair pairing together the move and the probability. And then the policy is just a list of these pairs, a list of moves and probabilities, right? Now, notice that we're not touching probability. We're only indexing onto 0. Like move and prob of 0 gives you the move. If we had 1, that gives you probability. But like we're only like kind of mucking around with the moves. The probabilities remain the same. Like right here, right? If you look at like the relative lengths of these velocities, like this is a very tiny velocity. This is a tiny magnitude. And then like when you flip it, the magnitude stays the same. It's still like low probability. And then, wait. No, sorry. I'm conflating, I realized, I'm conflating the direction with the probability. That is wrong. I should not be doing that. Sorry. What I'm saying right now is like we really want to launch this coin in this direction. I guess like right now the lens, because again, like when you launch a coin, the velocities we're doing, their magnitude is fixed. Namely, it is fixed to like 0.4 times the shared constants that max launch velocity, and then multiply 1.1 if you're a king coin, of course, giving you extra buff if you're a king. But the point is that like the move, like these components are in terms of directions, but then the lengths, I'm reflecting the meaning of these like lengths of this being like kind of tall, like longer, and this kind of magnitude being a less relative to this one, is that it's lesser likely to be played. Like if you look at leechess.com and like you're analyzing games, like they do in terms of like the thickness of the arrow, right? I'm doing in terms of length. Like, let me just play a quick game. I'm using a trackpad on my laptop, so I'm probably gonna suck. Okay, he just aborted. Okay, new opponent. Let me just play a quick game. Okay, a Scandinavian. Okay, let me just develop. Let me just get some center. Let me just go here. I could just like trade everything, or just bring something out. Just castle. Let's just move it here. Oh, he's gonna castle, right? Yeah, let me just trade everything. I just want to like quickly like end this just to show the arrows. Oh, did I just drop a pawn? Maybe there are like some discovered tactics where like I can check the king and then kind of win the queen back. Oh, let me just kind of quite a battery. Okay, he's blocking it, but now he's kind of relinquished some control there. I'm running out of time. Let me just kind of do that. Why not? Let me just slide my queen here. Pre-move that. Drop back. Wait, did I just... No, it's protected. It's protected. Okay, just trading everything? Alright, fine. Do I have any tactics? No, I don't think so. Let's just kind of solidify. Okay. Let's just create a one-move threat. That looks wrong. Now he's just giving me the default. Oh, okay. Greedy person. Let's just go to the 7th rank. Let me just go here. Might just have like a move there, maybe. Let me just go there. Centralized. Go here. Try to gang up on this pawn. Oh, also a threat there. Maybe he won't see it. Wait, what? Isn't that just me? Okay, I kind of feel bad about that, but let's go to analysis, right? So like here, like, sorry, like if you're kind of looking at like the arrows, right? Like they show like thick ones and thin ones, right? Like based on like, wait, is there a way to like? Maybe it's chess.com that has that thing. Yeah, like, so 1 out of 5. Maybe let's like show more. Yeah, exactly. That's what you do. Multiple lines, right? So here, like, do you see how like this arrow is thicker and longer, and this one is kind of like thin or whatever? So like this thing right here, these arrows are basically a policy distribution, right? Like it's saying that like black should really kind of like take this bishop. That's the main move with high probability, and these ones are low probability. Like yes, this has some direction too, like, but it's more like the amplitude, no, the magnitude of the arrow kind of like means that we really want to like. Let me just increase the number of lines to 5 lines or however much. Yeah, okay. So like here, like the candidate moves, like it's considering this, where this one has most probability to it, and these are more secondary, and that's like the thinnest. Okay, I guess the length is a bit. Okay, I see. Sorry, this amplitude does not mean anything. This amplitude is simply like describing the move, like take here and like move the queen 1 step and move the bishop like a Manhattan distance, or like move an octile distance of 2, and like move that of like 4 squares diagonally 2 squares. So like the length of the arrow in this case is not the probability. I'm mistaken. The length is just like describing the move. It's the equivalent of my like direction here. But then the thickness, like this one is super thick, right? Like this arrow is very thick, and then these ones are medium, and this one's super slim. Where like in Lichess, like the slimness, like the thickness corresponds to the probability of like the move. Whereas in my whiteboard, for me, like the length corresponds to the likelihood of the move. So like we really want to move this coin, like really want to move it towards the center, right? And when we flip it vertically, we still want to move this coin that was now in the bottom is now on the top. We want to move it to the center. And secondarily, we want to move this corner coin, the top left corner, a little bit to the center. And like here, we want to move it a little bit to the center, but we mostly want to make the move with the other coin. So that's why, like, what I'm saying is that the relative probabilities of the moves stay the same. Like, if we took this chessboard right here and we like kind of like we feel like flipped it about the other side. In fact, let's do that. Let's flip the board, right? You see that? Like we can flip the board. Like we can keep flipping the board. That's completely fine. We're allowed to flip the board however much we want. That does not change what the computer is telling us to do. If it's black's turn, we really want to make this capture, right? With highest priority. Like we should capture. And again, if we flip the board, we still should capture. So like it's the same piece. Like we want to move this bishop no matter how we flip the board. Just like we want to like we want to move this coin here, and we don't want to move that coin so much. Like we really want to move this coin. Same here, we really want to move that coin. And we kind of want to move that coin too. That's why this length here is like the thickness in Lichess. Like it's the probability. The direction, like describing the direction is sufficient to describe the move because everything, the move velocities are fixed in this turn-based variant. It's a lot of talking, but that's just kind of like explaining why like we're only consuming move to move. Like in the transform policy, we're only like when we're touching the move, we're only touching the move in the policy. The probability stays the same. We're only adjusting the components. We're only changing the angle of the move, right? We're not changing the probability. Like here, if we flip the board, the same thickness, like this bishop thickness, and like these relative thicknesses, like these thicknesses, they're staying exactly the same. That means the probabilities are not changing. Only the direction of the arrow like kind of changes, right? Where the direction and like the length, like the specify only like the move, like you get the point. The point is that thicknesses don't change no matter how we flip the board. That's the basically what I'm trying to say here. We don't touch the probability. Move and probability of 1 never gets touched. We only touch the move. Again, move and prob of 0 gives you the move. Move and prob of 1 gives the prob, but we don't care about the prob. The probs will stay the same. We're just transforming the move. And here are the kind of functions that transform the move. They do 2 lines, step 1, step 2, where we negate the relative components, and then we also have to correspondingly make sure the move IDs match the new velocity. Step 1 and 2, which I described like right here, like step 1 and step 2 we have to do for everything to transform the move. Okay, good. Now let's kind of go to the next one, right? Finally, what we do here is once we have done our symmetries, we have to kind of export them. So that's the last line, right? It's a spectacular line. Identity, flip horizontally, and then we actually have 2 more in BumperCoins, right? Where it's flipped vertically, like that. And then, at last, we have this last flip, right? Just like that. And I hope that this is correct. Let's check if it compiles. Compile TSC on symmetry.ts, right? Symmetry.ts. Okay, it worked. Get status, get diff, get diff. Good. And now let me just kind of commit this. Get add all, get log, copy, get commit, get status, get commit. Just kind of paste that message there. Test initial untested or untested work or untested work on symmetries for policy transformations. For policy transformations. Wait, is that capital or not? I don't think so. For policy transformations, hopefully symmetries finished because we export all of them. Okay, get status and I'll push it off stream. So yeah, I think that's good work. Again, all of this is untested. We're gonna use our scratchpad and like maybe make some tests visually, whatever, but like I think we're almost done. Like now it's just more like troubleshooting and testing and like debugging stuff. So let's I think I'll end stream here. I think I did a I described, I think I did a good treatment of policy transformations for symmetry. So I'll just kind of stop here then.